So I'll start talking about the JIT compiler of Ruby. My name is Kokubun. I'm from Treasure Data, and I'm a Ruby committer since the last year. I joined the committer as the ERB maintainer because I optimized the Haml template language 3 times faster, and then I made ERB 2 times faster. So I'm maintaining ERB, and then I'm optimizing the JIT compiler right now. So today, in this morning, Mats talk about the history of JIT a little. Here's a short history of it. And the man is called Vladimir Makarov. I call him Brad. Brad invented the MJIT framework to implement a JIT compiler for C Ruby. And but it was based on, his implementation was based on the new virtual machine called RTL. So it's a little not working for some edge cases. So I wanted to make it work for every situation. And then I created the another JIT compiler called YARV-MJIT. It's prefix YARV because it's based on the YARV. It's current Ruby's VM, name of the VM. So it directly compiles the current VM instructions to the native code. So it's compatible at least when the JIT is disabled. It's 100% compatible because I don't touch the VM implementation at all. So even after the JIT compiler is released in the Ruby 2.6, you can have 100% compatibility if you disable the JIT compiler. And as you can see from this graph, the YARV-MJIT was a little slower than the original MJIT based on the RTL. It's because I didn't touch the VM instructions. I can improve the performance by touching or crashing the VM instructions, but I don't want to crash the Ruby behavior because I'm running the production application with Ruby, and it's some serious application. So I want stability, and then I wanted to have such kind of a very compatible version of JIT compiler. Then I proposed to merge that in the last Christmas, but after Koichi and some other Ruby committers reviewed the JIT compiler, they found some bugs in it. So I fixed the bugs in 2 months, and it was merged the last February. And it's released in the same month. You can use the JIT compiler in the Ruby 2.6.0 preview 1. So it's a short history of it. So probably you want to know how to use it. And you can see how to use the option in the Ruby -- help. And usually you only need to use the -- JIT. That's it. You can see the many options in the help, but most of them are for me. So you only need to specify -- JIT. And if you run the Rails application, probably you don't execute the Ruby command to start the Rails application. So you may want to specify the JIT option in the Ruby opt environment variable. You can pass that via the environment variable. And the big difference after the JIT addition is the new optional runtime dependency, GCC or cron. As you can see, Ruby forks the GCC process, and you may see the GCC comparison when you run the Ruby. So it's kind of strange behavior of the new Ruby, but it's very good for our development and maintainability. And the above logs are printed by the JIT dash verbals 1, and you can see how it takes to JIT compile one method and what's the JIT compiled by some options. So the basics is that there is a thread to execute GCC compiler, and when there is a method, it's frequently called. It compares to the faster version of the method, and then it's compiled, and then the only fast version of the methods are executed. So it's the basics of the Ruby's method JIT. So you may want to know the performance of Ruby current Ruby's JIT compiler. It's the background. The background is money, because you can earn money by if the server can run faster. Because if the response time is 100 minutes, then it's become the 50 minutes. You can run the same application in half servers. So it's good for money. Then, but the actual performance of preview one was like this, and black one is the JIT compiler. So it's not fast compared to the non-JITed one. But this is current trunk, and preview one was there. So now it's much faster than the preview one release. So the preview 2 release will be much faster than previous release. And in some micro benchmark, it's now 5.7 times faster than not JITed one. And also, compared to 2.0, it's about 8 times faster. So in some micro benchmarks, it's very fast. But it's in benchmark called OptCarrot, it's very far from the 3 times faster. And even for the RTL-based JIT compiler, it's not reached to the 3 times 3 in my machine. In his machine, Ruby 2.0 was very poor performance, and it reached 3 times faster. But in my machine, it was not. So I want to make it even faster to run the Ruby makes 3 times 3 actual. So how to get there? And I implemented the Ruby method inlining. It was promising to achieve the Ruby 3 times 3, but actually it takes much time to compile when everything is inline. So I need to limit the methods to be inline at least, and also just inlining doesn't help to improve the performance, because actual optimization is done by the C compilers. And so we need to tell the C compiler how to optimize the performance. And currently, the generated code is very complex, and some optimization in C compiler can't be done in the current code. So I'm simplifying the JITed code, and let's see what we've done so far. So I want to introduce the preview one, optimization in the preview one at first. The most important optimization of the preview one was the basic inlining of Ruby method. Currently, it's not inline the definition. It doesn't inline the definition of the Ruby method, but it inlines the basic setup of the Ruby method. And I will show you how Ruby is behaving right now and how it's changed. And you may want to know this because if you understand this, you understand why Ruby is currently slow. So it's kind of interesting topic, isn't it? So by the way, I'm developing JIT compiler in my spare time because I'm not a full-time Ruby committer, and I'm doing this by just interested in why Ruby is slow. I want to know that Ruby is slow, and I'm developing JIT compiler. Anyway. So it's the kind of the interest of me. And when the Ruby method is compiled internally, it has the internal language called ISEC. It's instruction sequence, and it's just calling the bar method. So it puts the self to the stack, and it calls the bar to the stack top receiver, and like this. Oh, so ISEC is the sequence of the instructions. So there are 3 instructions: preserve and send and relieve, and then it calls the C functions associated to the instructions one by one. And when it calls the send instructions, there may be some types of Ruby method. There can be method implemented in Ruby, or method implemented in C, or attribute reader or attribute writer. So before we execute the foo method, we don't know what type of the bar method. And when, for example, if the Ruby method is the bar method is the Ruby method, the search method function caches the Ruby method implementation to the send instructions, and as it inlines the C function pointer of Ruby method push to the cache, we can JIT compiler can understand what type of the send instruction will call the method. So it's needed to for the JIT compiler to have the information in the ISEC, and we can't do the same optimization in VM because we don't know bar method is what type of bar method. And after it's inlined in the send instruction, call method will call the C function pointer of the Ruby method push. But if it's just calling the C function pointer, C compiler can't know how to optimize the just a function pointer. So we need to inline the actual definition of Ruby method push to optimize this. So it's a blocker of the Ruby's performance, one of. And so in JIT compiler, we can just inline the Ruby method push in the generated code. And also, we can skip the search method as well. So it's faster. So it's the first big jump from the basic VM performance. And using the method cache, we can bypass the search method search and also method dispatch. It means the calling the C function pointer. After we do this, we can also inline the definition of the Ruby method. So we can use this for a future very big performance big jump. And I want to introduce another optimization. And this is the definition of hash blanket method. It's just referencing the key. Its definition is like this. If it's an array, it calls the fast array implementation. And if it's a hash, it calls the hash version of the fast implementation. But if it's not a hash or array, it should be just a fast. No, it should be just an overhead. So we want to remove the hash or array check in the JIT code. So I did that, and it becomes faster for things like action control parameters. It's a hash-like thing, but it's not actually a hash. So we did array or hash check for like the parameters, but now it's faster than the VM execution. So it's some trivial optimization, but it's essential for Rails because Rails have many classes that has the blanket method. And another thing is related to that, and it was array method was actually external function. External function means the definition can't be seen by the compiler. And if we do this, I added another branch for the key argument. If the receiver is array and the argument is integer, it inlines the array integer left method. So it's now faster. And we don't want to inline all of them because if it's too big, C compiler can't optimize it well. So I only inline the very major branch. So that's the only 3 optimization in preview 1. And it's not so fast because I don't do other optimization. And I worked on improving the portability. I fixed many bugs in many platforms. So it took much time, and I also fixed the segmentation faults and deadlocks on very, and I also removed the broken optimization, aggressive optimization. So it's a little slow, but I reintroduced the, some removed optimization in the preview 2. So then I'll talk about the preview 2 optimizations. So this is the most important optimization in the preview 2. And I'll introduce how RubyVM is behaving right now. And just this is 3 methods. It returns only 3 number. It's convenient method. And it's compared to the put object 1 and put object 2, and it executes the plus instructions. So how it is executed? And RubyVM has 2 registers, program counter and stack pointer, and it's moved like this. So it pushes the 1 and 2, and plus, if the program counter points to the opt plus, 1 is plus to the 3. Then it's read and return the 3. But we want to remove the stack pointer motions, because if we continue to move the program counter and the stack pointer, we can't reach the performance of C language or some fast languages. So Ruby is slow because we move the program counter and stack pointers every time. So I want to stop this motion. And in original, very first JIT compiler, we moved the stack pointer every time. And this is assigned to the pointer and reads from pointer and plus for the pointer. And we always incremented or decrement the stack pointers. So it's overhead of our Ruby VM. And after it's JIT compiled, we can optimize it to the just C local variable. If it's a C local variable, it can't be referenced by other C functions, or even C compiler can inline the each value to the some opt-plus instruction. So it's good for optimization. But this strategy doesn't work for some complex cases, like I will introduce that situation. So this is some code, complex code, but we may not write, but it's simplified situation. So if the both error and 3 methods are JITed, this is the call stack in C word, and the C is always starts from the main function, and yes, it invokes the RubyVM, and in RubyVM it calls very important function, setjmp. Setjmp is needed to be called because we have exceptions in Ruby. So if exception is raised in the Ruby word, it calls a wrong jump function, and wrong jump jumps to the setjumped place. And that's because setjump preserves all information of the CPU or stack or any other registers. So it's called in there, and then 3 is pushed to the call stack. And if the variables are in the C, stack is implemented as just a C local variable, it will be pushed to the C's call stack. So it's placed there, and once the 1 is pushed to the call stack, and then error is called, it's pushed to the call stack in C, and when it reaches the RB raise, it will call long jump. And once long jump is called, it erases all the C function frames to the before the set jump is called. So we lost the one object in the C stack. So we don't know how to pass the 2 to each another receiver. So it causes a segmentation fault. So using the C local variable to the VM stack is problematic for this situation. So we only do this optimization when the method doesn't have the rescue or ensure or things like that. It's implemented as catch table internally. So if it doesn't have rescue or ensure or similar things, we can improve the performance. So it's the important performance optimization in the preview too. Then I also implemented another optimization. It's called so. So when Ruby VM is executed, it's called the setjmp method. But it's slow because it preserves all backtrace or register states. So it's slow, and we want to skip the setjmp call if we can do it. And if Ruby VM is already invoked and we call the JIT code directory, we can skip the setjmp call. So I did that, and now yield is 1.3 times faster. So let's see another optimization for the Ruby VM. I also optimized the program counter. It's like this. When this 3 method is called, program counter points to the phrase of the executed phrase, and it points to when it reaches the error method. Another frame is pushed to the Ruby call stack, and the errors program counter points to the error method, and it reaches the raise, and then raise is pushed, and it calls the wrong jump method function. And which wrong jump is called, it erases the raise and error call stacks, and the program. But we can start from the 1+2 because the 3 method frame has the program counter points to the error part. So program counter is needed to resurrect the state of after the exception is raised. So we can skip the motion of these arrow is moved. The motion of these arrays, arrows can be skipped if the method doesn't have the catch table. It means that it doesn't have the rescue or ensure or things like that. So we improve the performance in the method which doesn't have the rescue or ensure. Then I did other optimization like just adding the force inline attribute to some plus or minus or multiply or instructions. So it's good for optimizing it's good to let compiler to optimize many instructions. And in C compiler, it has the threshold to inline the function or not. If the function is too big, C compiler doesn't inline the C function, and some of Ruby instructions are too complex to be inline. So I needed to force the C compiler to inline those functions. And it contributes to the performance, like OptCarrot is optimized for frame per second. By the way, OptCarrot is a benchmark of the Famicom NES emulator, and after it reaches the 60 frame per second, it's done, but we are using it for just a Ruby benchmark. Then after that, I also inline the instance variable instructions. That's because OptCarrot uses instance variables a lot. So it's good for OptCarrot, but it also contributes to the Ruby's performance. Then I also disabled the stack consistency check. In Ruby VM, it pushes the object to the stack, and stack state may be wrong when the compiled code is wrong. So it always checks the consistency of the stack, and when the read instruction is executed, the stack must be 1 because any Ruby method can return one value. So it checks the state of the stack after the Ruby method is executed. But it's an overhead, and I disable the consistency check in the JIT code because it's already checked in the original bytecode. Then I also inline the attribute reader in this. There are many types of the method in Ruby VM, like Ruby or C method or attribute reader or attribute writer. And I then, after Ruby method push, I also inline the attribute reader. So when attribute reader is called, the operand of send instruction will take the cache. And if we have a cache in it, JIT compiler can detect the method is an attribute reader, and we can just inline the just getting the instance variable. So getting just an instance variable is much faster than calling the attribute reader, and then we can make it faster. So after this optimization, attribute reader is now made 4 times faster. So we made many optimization in after preview 1. So it will be faster than preview 1, but and also generated code is much simplified. So if we inline the Ruby method definition, it can be much faster. But it's still not enough for Ruby 3x3. I think Ruby 3x3 is good goal to be achieved, and it's well defined. So it's difficult, and I think it seems if even possible to achieve. So I think it's very good goal. Then, but we need to do many things to achieve the goal, actually. So I want to tell some feature of the Ruby JIT. The one thing is using the wrong jump to generate aggressive code. If we use wrong jump, we can erase the code stack frames. So we can generate the very aggressive code, speculative code to be executed only when some assumption is correct. And when assumption is correct, being wrong, like if trace point is enabled, RubyVM it converts all the bytecodes to the traced versions. So it's a very unexpected situation for JIT compiler. So currently JIT code has the GERD for trace point, but it's of course slow. So I want to disable that or remove the GERD from JIT code by using the wrong jump. Then I also have ideas to specialize the instruction of the generated code. I explained the implementation of the hash blanket or array blanket method, and that instruction have the type checks. And the type checks is some slow part of the Ruby VM, and I want to remove the checks for some types. And if we have some profiling or instrumentation in the RubyVM or JIT code, we can generate a faster version that doesn't have the check for types. Also, we have some Brad is planning to add some multi-tier JIT. It's 2 versions of JIT. So Java is doing some kind similar thing, and it's needed because if JIT compiler does every optimization, it takes much time to do or then finish the optimizations. So we can balance the compilation time and efficiency in the optimized code. After doing that, we can optimize in a very short time. So it's needed to people like who deploy application every 10 minutes. I think it's very frequent to deploy application every 10 minutes, but I heard GitHub does it. And also another idea is profile guided JIT. GCC has a feature to profile code compiled by the GCC, and in profiled version, it generates a profile result. And if we use profiling results to the GCC comparison, GCC can generate a faster code using the profile result. So it would be good for to introduce this kind of JIT compiler implemented with GCC. Then also, we need to improve the performance Rails because I'm also running the Rails in my company. And currently, even after the preview 2 optimizations, we can't still optimize or make it faster in Rails application. That's because I investigated the cause, and actually, the GCC is executed by the parallel thread, but it uses some resources of the CPU or something. And so during the JIT comparison, something becomes a little slower. So we may need to decrease the frequency of the JIT comparison to reduce the overhead of JIT comparison. And also, I'm planning to implement method inlining for C definition or Ruby defined method. So I already succeeded to implement Ruby method inlining, but I need to simplify the generated code to exploit more C compiler optimizations. So I want to do that by, I want to remove the code unrelated to the loop. So by doing that, we can reduce the calculation time for very hot thing inside loop. Also, we may be able to finish the calculation of the constants or retails or Ruby's constant by using the C compiler optimization. And also, we want to remove the many type checks. So, conclusion, and Ruby 2.6.0 preview 2 will be much faster than preview 1, but it's not still ready for optimizing Rails. So I'm working hard to improve the performance of Rails. And also, we have so many things to be done for Ruby 3x3, so probably the future will be much better than now. So thank you for listening.
Thank you. Do we have any questions from the audience? Can you switch on the intercom, please? Thank you.
Hey, hello. I have some question about the error rescue to the part, the no catch table.
Sorry. Which part?
How do I say? Number 1 or number 2, I think. Yeah.
This one?
Yeah, this one. But can we achieve optimization by inspect the block that has rescue block, and we can know if we will do some inspection. Can we do some evaluation of the code? Can we know about all the potential errors generated by error that ERR method will be catched by the block, and we don't have to jump outside the tree function.
So I actually implemented to have the guard for calling error or something because it's if the error has rescue, I had to call the setjmp even before the error is called to catch the exception. Sorry. So we need to make sure that C functions are not unexpectedly erased. And if we call the JIT method frame, we want to make it not erased by the long jump. And so if the error method doesn't have the rescue or ensure, three methods calls the setjmp. And also, if the error does not have rescue or ensure, it doesn't call setjmp because outer Ruby VM setjmp can catch the exception and handle it, because it's very complicated and hard to say, but Arito helped for your understanding. So could you repeat your some questions?
Can we talk maybe later?
Oh, okay.
Thank
Fine.
you.
If you have any questions, you can speak to the speaker late after this section. Do you have any more questions?
Hey, so you mentioned that the JIT is not ready yet for Rails, and it's a preview tool. So Ruby 2.6 should be released in December, which is 7 months from now.
Mm-hmm.
And do you know what's the plan if you're not happy enough with the performance? Will the release be delayed, or will it be released with just information that is not suitable for certain applications?
Whether Rails is slow or not will be included in the Rails note, and also probably of course the JIT enablement is JIT is disabled by default for at least for 2.6. So probably I think it's very backward compatible, and we don't need to make sure it's fast at least in 2.6. I think. So
okay.
Probably we release it for alpha testing or beta testing and make sure it works for many platforms, and gradually we can improve the performance later.
Great, thank you.
Do we have any more questions?
You said you want to go. You are going to remove the type checking, but it's very difficult to do in Ruby, right? How could you remove the type checking?
I'm not going to remove all the checks of types. I want to leave only one type checks, and if it's not met, we fall back to the another VM instruction. So if the type assumption is correct, we can execute a fast code. And what I wanted to remove is the many chain of the type checkers, multiple type checks. So if it first checks the hash and array, it will be slow, and I want to make sure the check is only once. Do you understand that?
But if you have an array of Ruby, every element may have different types in the array, right?
In array, different types.
Different types of objects in a Ruby array. How do you check that? You can do it in once.
First of all, the method dispatch. So it has another checks. Not only that, my slides are very simplified and it lacks some information in it. So it also has the method signature, so it can check it. It also check it. So it's not literally one checks, but I want to reduce the types of checks to one. Does it make sense?
Okay.
It actually checks the method cache. So, and the method cache is also used in the VM, and thus it should work. I can explain that further later.
Yeah. Okay, thank you very much. Well, thank you for our speakers section. And if you have any more questions, please feel free to talk to Mr. Kokubun-san after the session. And we do have an after party tonight at 8th floor. Okay, thank you very much for your section.